Welcome back to IT 3000, Episode 13. Today we're pulling apart one of the most elegant lies in computing, virtual memory. Every process running on your machine is quietly told the same story, that it owns the whole system, all of it, from address 0 on up. And here's the twist we'll keep coming back to. The address your program thinks it's using is almost never where the data actually lives. So let's give that lie a proper shape. Virtual memory is an abstraction where every process gets handed its own private, contiguous address space, a clean, uninterrupted stretch from 0 to some enormous number. Hardware then translates each of those addresses on the fly into a real physical location in RAM, or when that data isn't currently resident, into a spot on disk. One sentence to hold on to: every process is told it owns the whole machine, and the hardware quietly keeps that lie consistent on every single memory access. Maintaining that lie isn't free. Every memory access pays for a hardware translation. So what does that tax actually buy? 4 things. Isolation. A process can't even name another process's memory. It's not forbidden by policy. It's unreachable by address. Simplicity. Every program starts at the same layout so the linker doesn't have to relocate code at load time. Overcommit. Processes can ask for more memory than the machine physically has because most of it is never touched. And sharing, one copy of a library maps into many processes, and with copy on write, forking a process costs almost nothing. So let's follow a single load or store down through the hardware. The program hands over a virtual address, what it believes it's using. The CPU checks the TLB first, a tiny cache of recent translations, and in the overwhelming majority of cases the answer is already there, roughly 1 cycle. On a miss, it walks the page table in RAM to find the real physical frame, and only if the page isn't resident at all do we fall through to disk, and that last step is on the order of 100,000 times slower than a TLB hit. The whole system is engineered so you almost never pay that price. Now let's watch that rare expensive case actually unfold. The program issues an ordinary read, nothing special from its point of view. The TLB misses, the page walk finds the entry marked not present, and the CPU traps into the kernel. The kernel makes a judgment call. Is this a legitimate page that just isn't in RAM yet? Or is the program touching memory it has no business touching? If it's illegal, that's your seg fault, delivered right here. If it's legitimate, the kernel finds a free frame, evicting some other page if it has to, pulls the data in, updates the page table, and quietly restarts the instruction. The program never knows anything happened. It just took a few milliseconds instead of a few nanoseconds. Before we go further, let's untangle 3 words that get thrown around interchangeably and shouldn't be. Paging is the normal, healthy activity we've been describing. Individual pages moving between RAM and disk on demand, happening on your machine right now. Swapping originally meant something bigger, evicting an entire process from memory, but in everyday Linux usage it's drifted to just mean the disk area that backs paging. And thrashing is the failure mode, the system so overwhelmed that it spends all its time shuffling pages instead of running code. Disk pinned at 100%, CPU idle, nothing actually getting done. Everything we've covered today rests on machinery worth exploring on its own. The page table is the actual data structure holding those mappings. The TLB is the tiny hardware cache that keeps lookups fast. The MMU is the chip that performs the translation on every single memory access. Page faults, swap, and memory leaks each deserve their own episode too. But next up in the series, we're stepping one level closer to the CPU, into the world of cache. So if you take 3 things with you from this episode, let them be these. Virtual memory buys you isolation, simplicity, overcommit, and sharing, and the price is a translation on every single access. Isolation isn't politeness from the kernel. Another process's memory simply has no address you could write down even if you tried. And paging itself is healthy. It's only thrashing when the work of paging stops buying you anything. Every process is told it owns the whole machine. That's the lie, carefully maintained. Thanks for watching. I'll see you in the next one, where we go deeper into cache.